Todd, how you doing? Thanks for coming
Travis,
on, man.
how are you? No, thanks for having me.
Yeah, heck yeah. Stoked to talk because, I mean, LiDAR's everywhere. You're starting to hear it. You know, you hear it a while ago. It's on, some autonomous car. You're like, what the hell's LiDAR? What does that mean? And now it's coming on the iPhones, it's on the iPad. So I figured it was about time we learned what the hell this is.
Yeah, totally good timing. And you're dead right. Yeah. And it's been around since the early 1960s. So it's taken just a little while.
Yeah.
And it's been kind of, I don't know, stealthy growth from the mass market perspective. But I agree with you. Once it hits the iPhone, which, the iPhone 12, according to, and they haven't announced yet, but by all accounts, it looks like it's coming. And there've been some shots of that camera array in the back, and they've got another little dot there. It went from a triangle to a square, and
right, yeah.
One of them is LiDAR, which is a really remarkable thing to be able to squeeze it into that kind of space. But pretty cool.
Yeah, it's crazy stuff. Okay, so yeah, we'll get into all that stuff, but I think we should just start with kind of the primer of what is LiDAR. LiDAR. Can you explain it to us?
Yeah, totally. So the easiest way to think of LiDAR is that it is a measuring tape that's made of light. Right. So if you have a measuring tape, there's a little bit of what's the tape made of? Right. Forever, the meter was defined by a platinum bar that was housed in Paris, for example. Then they realized that the bar actually, it's nice to have a platinum bar, worth a lot too. But even subtle temperature changes will change the length of that bar. Laser light is a universal constant. Right. So the speed of light is the speed of light, be it out of a light bulb or a laser. And, scientists and engineers have figured out ways to bounce that light off of a target, and the target could be the atmosphere, it could be the water, it could be the land under the water, it could be my nose, whatever. A building interior, a streetscape, post-hurricane damage, whatever it might be from the air. And then time, most of these things work this way where imagine yourself throwing a tennis ball against a wall. Chuck the ball. Imagine the ball made no sound. Chuck the ball at a certain speed, catch the ball. If you know how hard you threw the ball, right, and you can time how long it took for that ball to come back to your hand, then you can calculate the distance with a pretty easy calculation, right? You don't have to do stereo vision or other more complex, computationally difficult processes to figure out how long it took. So a laser, what you do with a laser, the speed of light. There's a timing chip in the thing, so you send the pulse of light off and you wait for it to come back. The whole bit doesn't come back because things bounce everywhere, but it's looking for a particular color that it sent out, and it's timing how long it took to come back. So you do it onesie twosie, and you have a laser ranger, and that's kind of like radar guns that police used to use are now laser guns for the most part, and that's pretty much the philosophy behind that. But once you have that down, there's a billion places that the thing can be taken, technologically speaking. And the Apple, ability to scan a room is one manifestation of that. Instead of one, they've got a grid of laser, it's infrared light that bounces off whatever it is that you're taking a picture of, so to speak.
So it's instead of just kind of one laser, it's multiples being shot out?
And a lot of these things will work. It's often one laser that hits a splitter and it goes in a bunch of different directions. And, God knows that engineering is miraculous that they can make these things work. But there's a detector associated with each of the beams that split off of this single laser, say. And the detector knows which of those beamlets, which of the photons, the light packets, the light tennis balls, if you will, it's supposed to look for, and the one next to it's only supposed to look for the one from the one next. I mean, it's when you get into the actual engineering of these systems, it boggles the mind. And they're doing this. The higher end laser scanners, be it on a tripod now or from an aircraft, will do millions of pulses per second. Meaning, if you're flying at 15,000 feet or whatever it is that some of these systems do, they're kicking out multiple pulses that are in the air at the same time, bouncing back with multiple beamlets and multiple. I mean, it is crazy that these things work as well as they do, and they really do work. So, I mean, we just covered a little bit of ground. Does that help you understand sort of what LiDAR is all about?
Yeah, because I mean, it's not. It's similar to like a radar or something where that's sending off radio waves and then seeing how long it comes back.
You're dead right. I mean, radar is, so you talked to Jeff Hecht, who has done a bunch of really good books on lasers.
For folks listening, yeah.
Yeah, episode 47. And the deal is lasers emerged from the radar world after World War II. And it's a different technology to create. But essentially, yeah, I mean, radar is all about bouncing radio waves off of stuff, and back they come, and you can decide distance and to some degree make out what something might be. The big difference between radar and LiDAR is that LiDAR uses light. And so a light wave is 100,000 times roughly smaller, a light wavelength, than a radio wavelength. All of them it's all electromagnetic waves, right? You go from radio waves to gamma rays, and our visible light is basically one key of the piano keyboard breadth of the light spectrum.
Right.
All this other stuff from side to side. So the radio waves are big fat waves, and light waves are getting pretty tight, right? Well, if you have a really small wave, then you can resolve or see stuff that a radar wave can't see. So that's the real, people are into LiDAR in the automotive space, for example, because a radar combined with a camera can do really good stuff. And you could argue that if you have visual system, stereoscopic or whatever vision system, that it's as good. And some people will argue that. But you can really resolve stuff. So you can scan someone's face and it looks like their face. The colors are off because it's essentially a bunch of math that's coming back from the scanner, but it takes a little bit of processing. And you know the exact length of like my nose or the eyebrow hair or whatever, depending on how close they are.
Wow, it's that accurate.
It's the same concept as radar. It's just squeezed down. And sonar for that matter. So it's sound waves with sonar, and those are great big long waves, and it's not electromagnetic. And so, you know, you can tell a distance with sonar, but you can't really resolve much of anything. Have you ever seen a fish finder on a boat? You ever been out on somebody's that had to have, you know, a little screen that allegedly shows fish? They can't resolve the fish. There got to be a few fish there. There's some blob there.
Sure.
Because those sonar, the sound waves are too fat to be able to recognize what's what.
Man. So is there any opportunity to go past light waves into like a smaller, more accurate, or is that not even really necessary?
Well, they're already using ultraviolet, which is a little bit tighter wave, a little smaller wave than the visual spectrum. And most of the LiDAR that's out there that we would see out there on a car or the iPhone or radar detectors, they use infrared. So we can't visibly see it. It's still certain wavelengths in the infrared can do damage to your eyes. So they got to be a little bit careful about what wavelength they use.
Right.
So they're already kind of going from side to side. The issue is if you go tighter and tighter, you get into high energy infrared, which you're damaging stuff, X-rays, gamma rays. So essentially, you could probably get a super, super accurate gamma ray LiDAR. Problem is it would kill your target. Which,
yeah, sure.
You know, depending on the target and maybe the person sending it, because some of those are going to bounce off the target.
Right. Okay, so it makes sense. Man, so this is cool. And then I guess, so are they sending off, you kind of mentioned it, but like different, like they're all, you know, infrared or something like that, but are there different frequencies that they're sending off for different reasons?
Yes, absolutely.
Okay.
So a good way to describe it, an easy way to easy with lasers, you know, and LiDAR, easy, you use the little quotes.
Yeah.
If you're doing bathymetry, which is to measure one of the really useful uses of LiDAR that you and I wouldn't have been aware of, but it's super important, is understanding how deep near shore water is, up to a few hundred meters out. So you can't put a sonar boat in super shallow water, right? So the military is interested in it because the Marines, you know, they land on beaches, and beaches are a really funky environment because the sand moves around and it's too shallow. So you've got to penetrate the water to understand what's underneath the water. So the classic LiDAR that's used for mapping, so aerial mapping, say most mapping, is an infrared LiDAR. It bounces off water typically. Then they use a blue-green laser at a different frequency that goes through the water. And then you can determine the depth of the water by subtracting the stuff that's bouncing off the top of the water, the infrared, from the visible green light that goes through the water. And to get there took like 30 years of really smart people figuring out the lasers, whether it'll go through all the turbid crap that's, you know, in a river somewhere or a shipping channel. And then the math behind understanding, well, if water's typically a little cloudy, right? There's just crap stirred up or whatever. There may be seaweed. So they mathematically have figured out over decades how to subtract out the seaweed, how to adjust for turbidity, which is basically a sandstorm underwater.
Yeah.
But a good question. And those are two different wavelengths. They use so many different wavelengths for so many different uses. Another really interesting one is, and I don't have this in my head. I had to study up for this, but one of the uses of LiDAR is to, from like the South Pole, where it's very clear, they will shoot a laser about 50 miles up to what's called the mesosphere, which is a really high atmospheric layer where there are sodium atoms floating around and iron atoms and potassium atoms, whatever. Well, sodium lights up at 589 nanometers. So they calibrate the laser to light up sodium. And by looking at the sodium, because it's essentially making it glow, right?
Whoa.
If you make something glow 50 miles up, there's a couple things that can happen. One, what's up there. There's sodium up there. But two, because of the Doppler effect, which is like the police car goes by and it sounds like a high-pitched thing and then it goes quiet, it goes lower.
Right.
They use that with light too. It's squeezing or pulling the rays depending on the motion of whatever that you're measuring, because the speed of light's a constant. So the only thing that's changing is the frequency. Don't want to get too into this, but it glows, and then they can see if it's moving, they can recognize the wind, and then through another mechanism, they can actually take the temperature of something that's 50 miles up, which is a really tough place to measure stuff because balloons don't go that high and rockets don't want to go that low. And finally, with the color thing, the Keck telescope at Mauna Kea, and these gigantic, 10 meters of glass that reflects whatever. Uh-huh. Those things are useful to us because of a spin-off of what I'm talking about here. So these upper atmospheric scientists were making sodium glow, right? Yeah. Well, if you make something glow in the sky 50 miles up, it looks a little bit like a star, correct?
Sure.
You call it a star. Well, they were like, some French scientists in the mid-'80s postulated that if we could make something glow up there, we could use it as an artificial guide star for our big telescopes. So I don't know if you've heard of adaptive optics. No. But a telescope on the ground has a problem, and that's the atmosphere. It's turbulent, right? So Hubble is a great thing because it's above the atmosphere, and stars don't twinkle when you're above the atmosphere. Twinkling is from the atmosphere, right? That's a big problem if you're an astronomer. So these guys kind of turned that atmospheric LiDAR on its head, created an artificial guide star that then the Keck telescope, while it's in operation, is focusing on to some degree. And there are these mirrors that have little actuators in them that counteract, if you can imagine this being possible, the turbulence in the atmosphere so that the end image is completely still. So that's why these massive telescopes are actually functional on the ground, and that they're still building big ground-based telescopes. Because otherwise, if you had twinkling, it would be extremely difficult to just, mathematically do away with all that right. Moving around. So
holy crap.
Yes, that's why I had a lot of those holy crap. When I'm reporting this book, I'm like, well, that's a holy crap, and then that's a holy crap, and so yeah.
Dude, it's amazing. Yeah, because it when you can kind of explain it like that, and they're bouncing off mirrors and stuff, it sounds like it makes sense how they're doing it, but to actually do that it's being done is mind blowing.
It's astonishing. I mean, and that's where you recognize that sometimes in our political moment, you wonder if anybody has any brain at all, right?
Right.
And then you start to talk to people that do this kind of work, and you realize, we have a lot of problems, but we have an enormous amount of brain power. And looking at the pandemic, for example, those kinds of brains are working on vaccines also, right? Mm-hmm. They're working on that kind of cognitive power. So I think it's a reason for optimism in many ways.
Yeah, very true. And I'm glad, people like you are around to write on it and help explain it to dumb people like me.
Yeah, well, I'm always the second smartest person in the interview. So, I mean, and it's probably the case here too, Travis. But it's fun. I mean, it's very interesting. And it's the creativity and the, the evolutionary, the evolution of these technologies from, how one scientist takes one thing and somebody over here says, hey, that's really cool. We could do that with this. And it's really interesting. LiDAR is an interesting window into how science works. The cross-fertilization of scientific ideas. There's several examples of that as I reported. And I had no idea of this when I went into it. And then LiDAR, to be honest with you, is, for me, has been really educational to write about. And I hope that readers get the same benefit in that if you kind of follow the flow of LiDAR and its evolution as an enabling technology, then you get insight and understand like glaciology and, forest science and how the autonomous vehicle world got rolling, how 3D scanning, the 3D scanner that is used in the Marvel movies so they don't have to destroy the actual Times Square. That evolved from all this stuff too. So it's been pretty cool.
So, yeah, okay. So let's dive into some of those uses. So I guess, how about for specifically the Spider-Man thing? So they're just scanning Times Square and then recreating it digitally?
Yeah. Yeah. So what they can do now, because these scanners, they started with one photon, or, not one photon, lots of photons in one little pulse, and then you measure. Well, now they've got arrays of lasers that it'll be on a tripod. They'll push a button. I don't know if they duck or what, because the thing spins around, boom, and will capture everything around it. And maybe you put the tripod in a couple different places if you're measuring something where there's your view's being blocked.
Sure.
And then they can push another couple buttons, download this enormous amount of data, and then often put it through a CAD program. They have visual cameras that are on the same mount that are pulling in the color data and the actual, image data.
Oh, yeah.
And then boom. Truly, and there's post-processing that has to be done, but a lot of it's been automated over the years. You have a 3D photorealistic scene. And you can use a camera to do it too. But what the deal is, if you know the depth of every point out there, then you can move through the scene without having to do any additional work, because this point is here. So here's your point. Yeah. I'm moving from point A to point B, and that point is static. The point is still there. We know that that point is in XYZ space, in 3D space. So that's how you get these scenes that look like, oh my God, they just blew up Times Square without having to do that. And they did that, there's a company called Direct Dimensions that I write about. They'll use LiDAR, they'll use other techniques using tons of cameras also. And they scan the actors, they scan the outfits, and then they can do whatever the heck they want with them. You don't really want to kill Chris Hemsworth or whatever for your deal. And they never have had to, but it certainly can look a lot. These movies are so realistic now. And that's part of the deal, is the 3D rendering work that goes on in advance so that the mind can be completely tricked into believing what they're seeing.
Right. Man, that's amazing. So they can even scan an actor and get a perfect 3D or digital representation of their face.
Mm-hmm.
Jeez.
Absolutely. Yeah. And actually an interesting use that I visited these folks there in Owings Mills, Maryland, outside the DC area. And, they just do all kinds of stuff. They'll scan older military vehicles like the UH-60 helicopters. A lot of these things were designed on paper back in the day, and they're still in operation. So they'll go back in and scan the cockpit so that they can do CAD drawings based on those scans and speed up the upgrade process, for example. So that's one thing. The artist Jeff Koons, who does the big silver-looking bunnies,
oh right, yeah.
He's a sculptor. He uses these folks to do these highly, highly precise digital renderings that feed into his work. And then you mentioned the face. So they've got, I think it's anaplasty is the name of the medical field. But let's say I lose an ear, whatever happens, an industrial accident, or God knows, I'm Van Gogh. Well, Van Gogh cut his ear off in 2020. He could go to these folks. They would scan his other ear, and I don't know if they'd use the laser or not, but they'd basically take a digital scan, 3D, and then rather than have an artist somehow, in the old days, they'd be like, okay, the ear looks like that. Well, we're going to, they just mirror that scan. And then boom, you have a silicon mold and the other ear is in perfect condition. And they have it looks like a little medical area. They'll do all kinds of facial and other features. So
holy crap. Yeah. The uses are like endless. So when they're doing that kind of stuff, like how tight is the resolution, I guess, that they'll scan it?
You can basically, I think you could go to, sub-millimeter easily, especially in an environment where you are in a fixed tripod. And that could, again, sometimes they use cameras for these things. But with a laser, for example, you just scan it over and over and over. And if the person's not moving and the laser isn't moving, then you could get to an accuracy that, you'd have the pores, you'd have as much detail as you need. I think they don't need that kind of detail for an artificial ear, because people aren't going to be right up to your ear saying, "Now wait, is that your real ear?" But yeah. So, and it was just like, one of the challenges with writing this thing is like, well, that's really interesting. How does that fit in? Because you could make something that was absolutely 100% eclectic, and there's no connection between any piece of it. And I think, the story of LiDAR really is a series of short stories in many ways, and that's kind of how it's written. But the surprise is that there's all kinds of overlap between the different stories, which is what makes it fun, right? Otherwise, you're just a Wikipedia article or multiple Wikipedia articles on different LiDAR applications. And it's really the people that did the development and the problems they had to solve that make for the stories that make it worth reporting on.
Yeah. So what is kind of can we jump back to kind of the history development of LiDAR?
Yeah, let's. So the most fun fact about LiDAR is that it was conceived of in 1930, and the laser was invented in 1960. So there was an Irish savant who was probably on the spectrum. He would probably have been diagnosed with Asperger's today, named E.H. Synge, Edward Hutchinson Synge, S-Y-N-G-E. And he lived with his parents into his 30s. He corresponded with Einstein on some of his ideas, and Einstein actually responded to him. In the early 1930s, when he was in his late 30s, he published 3 or 4 articles in something called Philosophical Magazine in London. And Philosophical Magazine is something to do with philosophy. Natural philosophy was what they called physics back then, basically. So this guy, Hutchie, was his nickname, and the book opens with him. Imagined using World War I, zillions of World War I surplus searchlights, giant lights, to illuminate the upper atmosphere. Because again, balloons couldn't get up there. At the time, in the 1930s, meteorology, they understood that most weather came from the lower atmosphere. But even now, there are interactions between stratosphere and the troposphere, which is what the lower atmosphere that we're breathing is, that we don't quite get, right? So he says, let's use these surplus searchlights, blast the sky, and then we'll have elsewhere a photodetector, which basically takes light and turns it into electrons that can be read by an oscilloscope, or these days all kinds of different ways, right? So essentially he used, and this is a thought experiment, didn't do it. Nobody, 1930, nobody was going to go out and use hundreds of searchlights, whatever. But several years later, Carnegie Institution in Washington and Naval Research Lab scientists independently, although in sequence, so they used each other's learnings, proved that it would work, essentially. And so they had searchlights, and so they're using searchlights as their power source, as their light source, and blasting the upper atmosphere, and then looking to see basically particles. What are the aerosols? We've heard about aerosols with COVID, right? It's the stuff that you don't want to be breathing in. Well, those are all over the place in the atmosphere. So that's how it started. And then right before World War II is when it was starting to get proven out. People were like, hey, we could really use this to understand what's in the upper atmosphere. And I mentioned the sodium thing, right? Well, if you have certain wavelengths, if you know what your laser wavelength is and you tune it to a certain element, we can figure out what's actually up there. That's pretty cool. How much oxygen, how much nitrogen, say, based on the way the light bounces back. I mean, how they do this is nuts, but they do it.
Yeah.
World War II happens, right? So the guys that were working on this stopped working on it, and that sort of put it to bed for a little while until the early 1960s, when Ted Mayman at Hughes Lab, Hughes Aircraft time, in I think it's Palo Alto is where they are, invents the laser. And suddenly it's like immediately everybody was like, because they knew from radar, right? They squeezed radar into microwaves and smaller and smaller and smaller wavelengths. And they knew that if we had a tighter wavelength, we could do A, B, C, and D, but they just didn't know how to make a laser. As soon as the laser got made, atmospheric scientists picked up where Hutchie left off. And Hutchie had died in 1956 in an asylum, as it turned out. He never saw this come to fruition. Oh, man. Yeah. And started, everybody that did laser science in the early days apparently wanted to use an anti-aircraft gun thing. So they painted the anti-aircraft gun thing white, and they would seriously, they'd borrow a laser from somebody and, photo detect. Everybody had photo detectors this is SRI, which is Stanford Research Institute. Institution, I think it is. SRI today. And they started hitting pollution plumes and starting to try to figure out what can this laser see. And they realized that, we can see pollution, ground level pollution. And we can see clouds. What's the cloud ceiling? Well, we can measure that really exactly now. Stuff like that. And at the same time, they were using them at MIT. There was a team that did a project called LunaSea, LUNA space SEE. It sounds like lunacy. Their goal was to shoot the moon with a laser, which they did in 1962. And that work led to further upper atmospheric research. One of the scientists that was involved in hitting the moon, which is really just a technology demonstration, was like, we're seeing reflections off of stuff 80 miles up, right? What is that stuff? So that's how it kind of evolved in the atmospheric side. At the same time, Hughes, the military contractor, has this laser that can measure things 100,000 times more accurately than radar. That might be useful because we do fire control systems for the M60 Cold War tank. So let's integrate that. So they did a couple of technology demonstrations with something they called the co-LiDAR, COLIDAR, which was they put the electronics in a Cub Scout backpack and had this hokey looking, it looked like a weird double-barreled shotgun, but it was really accurate. And they modified that, and the Defense Department was like, that's pretty useful. And suddenly they have a pretty good business based on lasers. So you started with military contractors developing it, atmospheric scientists getting into it. As soon as the atmospheric guys, both lower and upper atmospheric guys, got into it, they started recognizing the potential value in bathymetry, meaning measuring the underwater land, if you will, the coastal mapping, and then it just went on from there. I mean, and vehicle autonomy, because we should definitely talk about that. That got going really early too. They weren't using lasers at the time, but they were trying to do the perception systems for self-driving cars in the early 1960s also. A lot of it was funded by NASA, trying to figure out, whether a moon rover would work.
Right, yeah. So they were ready, they were looking for this, essentially right when the laser was invented. They were like, let's use it for a LiDAR type of purpose.
Absolutely. Yeah, it was Hughes' first laser product was the LiDAR.
Yeah.
That I'm aware of.
Is this Howard Hughes or is that?
This is Howard Hughes' company, yeah. Hughes Aircraft, which then Hughes doesn't exist. It got bought by Boeing. But Hughes made satellites forever and ever, and a lot of communication satellites were later made by Hughes. They in all kinds of military programs. But Howard Hughes' company.
Yeah, crazy. I mean, I got the Spruce Goose dome that he built it in is out, and I see it on my walk with my dog every morning and stuff. And
really?
Yeah.
Oh, that's cool.
Yeah, he's all over the place. There's Howard Hughes Drive down in El Segundo, so he's all over here still. Yeah.
Oh yeah. No, I mean, and it's part of Boeing now, but I mean, the work that they did has continued. So.
Mm-hmm. Yeah, man. Well, that is super cool. And then, it's so interesting how someone will see kind of the technology and then they're like, well, shit, we can use that in our field for what we're doing. And it would be so helpful for this, you can see how it just kind of naturally spreads into all these different things.
Yeah, and there's some really fascinating examples of it. I mean, if you're game, I mean, I can give you a couple of things that I think they're particularly interesting. I mean,
hit me.
You had a team at NASA Wallops starting in the late 60s and 70s that were messing around with LiDAR, and we're talking these are huge. I mean, you've got a LiDAR in an optics package in an iPhone or an iPad Pro right now, right?
Yeah. These
guys were working in what were 80-person or 40-person in other uses, commercial aircraft that were crammed with laser tables and hard drives that, there were 2 megabyte hard drives that cost, $100,000 in today's money or something. I don't know.
Right. Yeah.
But a lot. Just everything was huge,
so
massive. Funny. But it's a testament to how courageous they were to some degree. Like it's kind of like the moon landing in 69, like the Apollo program. Like considering what they were working with technologically, that they managed to do that is truly a testament to the brain power and the courage that they had. And it's the same thing with LiDAR. So they would fly these things in a plane. It was called the AOL, and it's not the dial-up internet company. Airborne Oceanographic LiDAR. So they were trying to measure depth, right? for NASA, NOAA, and whoever else. That thing evolved. They started using different wavelengths, right? And I mentioned how a green laser can see into the water, so they're using those, and infrared, they're experimenting, doing different things. They flew over forests sometimes, right? And they noticed that they'd have to fly over the forests in the fall or the spring or the winter when there were no leaves, because the leaves were blocking a lot of the light, but some of the light was getting through. Well, forest experts recognized first in Russia and they published in Russian, so it was independent discovery, and in the United States. They were like, well, if the tree's blocking the laser, a lot of it, because some of the pulses would get through, then we could use it to actually figure out what's in the forest. Like, what's our forest made of? What are the competition? How much wood is there if you're a company that is, Weyerhaeuser or something that actually that sells lumber or makes paper? What are the habitats? How much biomass? And this has become a really interesting question recently. How much biomass is in that forest? And is it taking over time? If we do it over time, is it absorbing or is it letting that carbon go? The biomass, so it has to do with climate change and your carbon balance over time. If you have forests that are sucking up gobs of carbon, then maybe, and we shouldn't probably not get too comfortable with this idea, because it appears that forests are not sucking up as much carbon as we would like, or as would be nice for humanity. Then maybe you don't have to be as strict about whatever other mitigation measures as far as carbon emissions goes. So anyway, the forest guys get a hold of it and they think, hey, this is really cool. Well, at the same time, the military's got it, and they're like, well, if I can see under the canopy, I could see a tank under the canopy, right? So the military is at the same time developing the technology independently to spot God knows what underneath jungle canopies or whatever. Then, and this is interesting as any of it, archaeologists get into the game. And in 2009, Arlen Chase and his wife Diane finally hired out a plane that had a LiDAR in it. And they had been at the Caracol site in Belize for 20 years. And they had characterized like 2 square kilometers because it is dense jungle. You can see nothing. I don't know if you've ever done a jungle trek. I mean, it sounds really romantic. You get into the jungle and it's like, there's nothing 4 feet that way I can see nothing, and 5 feet that way I can see nothing. It's a lot of work to see anything. They fly over this thing with the LiDAR, and they characterize in the span of like 5 or 6 or 9 hours of flight, I think it was, total, a few different flights, 10 or 100 times the amount of terrain that had ever been characterized in the area. And the chases at that point, this is, again, 2009, there had been some minor archaeological uses. You had a Stonehenge guest on some time back. The Brits had actually overflown Stonehenge and found, you can see the undulations of the land, and stuff that people make is usually linear, right? It's a fixed shape. So they found all kinds of new hedgerows and former hedgerows near Stonehenge in the early 2000s. The technology wasn't really there yet. The Chases had been arguing that Mesoamerican culture, so we're talking about the Maya and so forth, was on a par with ancient Greece or ancient China. Big, not little villages, but really big. And they thought that, they didn't even have the wheel. They were using burrows and whatever, because it's so hilly. You're basically going to roll to the bottom of the valley every time you push something with a wheel on it. They said this has been terraced extensively, we think, and we think this was 150,000 people and not 5,000 people. And their colleagues were like, whatever, man. What? No. They've overfly this with LiDAR, and they find, I don't know how many structures that they hadn't seen. Arlen Chase told me that there were things that were 5 feet away from him that they had characterized 10 years earlier that they didn't even know were there. And the whole thing had been terraced, right? And there were roads, essentially elevated roads that were leading from place to place to place. And subsequent scans nearby in Honduras and elsewhere have confirmed that this is an enormous civilization that had been extant there. And they did the same thing in Cambodia. They've done the same thing in Europe to some degree. But I think the Mesoamerican story, as far as LiDAR's impact on a different field, or on a field that you wouldn't think that lasers would be terribly involved with, was pivotal there.
So the forest is just so overgrown, even when you're kind of right on it on the ground, you don't even notice this stuff.
Yeah. And if you think about it, that's a big part of it. But it's also just your perspective. You're right in the middle of it. It's really hard to get a sense, like a terraced field, especially because the terrace it's been overgrown, so it's not as easy to see anymore. And this is really difficult terrain to go through. So it's the forest for the trees issue too, right? That's why, is your manager always smarter than you are at work? No, but a lot of times, you'll go say, hey, I've got this issue, and they're just coming at the problem from a different angle. And so a lot of them will be like, if you thought of this and you didn't think of it because you're so buried. And that's, I think, LiDAR with archaeology to no small degree was successful because it pulled it all back and said, this is what's here. Now, they still need to get on the ground and say, oh, wow, there's a new temple over here. We got to check that out.
Right, sure. And it's just kind of exposing things.
Yeah, exactly. So it's the sort of first pass. And then they can go in and do the actual field work that is still indispensable, right?
Right. Yeah. So how does that, is it like, if it's such a dense, covering, how does that work? They just have there's a certain wavelength that can get through leaves generally?
No,
or
very good question. So what happens is there's so many pulses, right? They are, you really can't conceive of 2 million or whatever pulses per second, right?
Yeah.
So invariably, imagine just a crazy ass rainstorm, right, in the jungle. And yes, it's not a perfect analogy because the photons don't break up and drip and whatever. But here and there, you're going to get a drop that manages to go straight through, right? And and that drop is millions and millions of photons, of which on a muddy, whatever, forest floor, dirt or whatever, biomass everywhere, leaves, not a lot of them are going to bounce back, but it tells you how many photons are in there, that some of them make it back. So the vast majority of those light packets are going to hit the canopy and come back. And then every story on the way down, that's why the guys that do forestry are interested in understanding forests, because it'll hit the branches all the way down and the signals get weaker and weaker. And then there's a really strong signal, stronger than you'd expect from the ground level, because even in a dense forest, there are certain areas where the trees have been knocked down and they're shorter things. There's some scrub on the ground. And so on. That's how it works. But while you're on the topic, and I won't go on too long about this, they're combining LiDAR with other sensors in really creative ways. And one of them, that's another Carnegie Institution thing. A guy named Greg Asner has been doing this for years. I think he's still at Carnegie, where they have a LiDAR to do what we've been talking about. And then he's got a spectrometer, which a spectrometer is basically using light, in this case, not laser light you're shooting at it. It's passive, meaning it takes sunlight and then looks at the reflection from that sunlight to recognize, because the spectrometer can tell what something is made of based on the light that hits it, or that reflects off it. They can tell what the different types of trees actually are and things like that. They can characterize the forest, not only in terms of its height and its density, which the LiDAR is really good with, but also what the hell that leaf, because a leaf of a maple tree with a spectrometer and somebody that really knows what they're doing looks different than a birch leaf or a honey locust leaf or a blade of grass.
Wow.
So, yeah, the specificity is really remarkable. So these really powerful tools.
Yeah. Man, that's crazy. But then just to jump back, so when they're they're specifically looking for, ancient type of ruins or cities, and they get all that data, do they kind of have to clean it up to get rid of all that stuff on top, all the trees and canopy and everything?
Yes, they do. And that's done. So there's software. So the LiDAR will just send you a blob of stuff, right? And so the temple below, or the tank below the leaves, will initially, if you were just, our eyes don't make sense of it anyway, first of all. But if they did, it would be indiscernible. But they know, because again, from our tennis ball against the garage door analogy, once you do it a few times, you have a sense of sort of where the door is, right? And so if you were to get a reading, let's say somebody walks by with a board, and the photon comes, the tennis ball comes back way too early, you'd be like, that's a little weird. So they have software basically that says anything above this point or below this point, just put it really simply, and they're really sophisticated algorithms. I mean, people with PhDs work on these things for like a career. But they'll just say, okay, let's filter that out. We don't want the stuff that's up here. We don't want the stuff down here. And then they can move it around a little bit and say, oh, well, that's a really solid object versus something that seems like it's small. You can tell size, you can tell. So yeah, there's a ton of post-processing. And that's been and I would say today remains the biggest hurdle with LiDAR systems. And that is, it returns gobs of data. And for you to be able to process that, you need to take that gob of data and turn it into something that is less of a gob of data, or filter out the stuff you don't want. Right. So.
Yeah. No, thank you for explaining that. Cause I was always confused of how that would work. Cause light has to have a clear path. It has to, cause it will bounce off of almost anything, I guess, except for, water, or you can filter it through different things, I guess. But, that was confusing to me. So thank you for that.
No sweat.
Let's talk about self-driving cars. Can we get into that?
Yes, because that's what got me into this originally. So I'm from Dearborn, Michigan originally. Grew up, my grandfather's worked in the auto industry, my dad worked in the auto industry, and so on. Cool. As a journalist, I do not drive a super cool car. That's how it works typically. Yeah. But I'm still interested. I'm interested in the industry. And the laser that's changing the world bit, when I conceived, I didn't come up with the title, actually the publisher Prometheus did. And I thought I was like, that's really kind of bombastic. And then I thought about it and said, it's actually not too far off when you think about some of the uses we've talked about are pretty profound. But from a day-to-day perspective, self-driving cars are going to change a ton, right? I mean, I think they figured out that if people use robo-taxis widely, like Ubers with no driver, once they get this working, you could potentially get rid of 2,200 square miles of parking lots in our cities, which is the equivalent space of New York, LA, Chicago, Houston, and Phoenix combined. I mean, massive amounts of. So that's a big deal, right? And we drive our cars 5% of the time, roughly. 95% of the time, they're just sitting there. They're expensive. They break, et cetera. We don't really all need a car. There are people that definitely need cars. We don't all need a car. So that's what kind of got me into it. And the evolution of the technology. So to start, self-driving, LiDAR is an enabling and one of many enabling technologies in self-driving cars. The big deal is what goes on in the brains of the self-driving computer, or whatever you want to call it, right? It's the software. It's mostly machine learning now. That's what really is going to make this work.
Sure.
But you need to be able to see your environment. And it's garbage in, garbage out. So to do a modern, and we'll bounce back to the beginning, but a modern self-driving car, and we're going to accept Tesla, meaning let's not talk about Tesla, because Elon Musk thinks LiDAR is a crutch, and perhaps he'll be right in the long term. But as we'll hopefully talk about, LiDAR has been really instrumental in getting self-driving autonomy to where it is today. You need to do it. You need something that can see and really well, and you need much more data than we need. We really just need our eyes, our ears occasionally if there's a siren or something. But it's really our eyes, because we have evolutionarily been pushed through a process that allows us to take a million shortcuts to recognize our environment with depth and react quickly and all this stuff. A computer is not born with this. No one's, we're kind of born with it.
Right.
I mean, I taught my teenage daughter how to drive, and you recognize maybe we weren't born with quite as much as I thought we were, because I forgot but we're born with a lot of it. Computers aren't born with it. So you got to give them a lot of input, right? So they use GPS data so that they're very accurate street maps. So it knows what street it's on. And we see that with our maps on cars that are not autonomous too these days. You also use radar, because it's cheap and it can see stuff very well. It's a very, very well understood technology. A lot of them use ultrasound also. They'll use magnetometers to see if there's more ultrasound now. So it's essentially waves bouncing off of stuff. And the missing piece for a long time was visions. Cameras, obviously, is we should probably put that up first. But cameras are really hard. Vision systems are hard. They're getting it now to degrees that are probably stunning to you and I, to you and me. But it's hard. Vision, it takes a lot of computer processing, and as we talked about these guys filling airplanes full of computer equipment, right? You couldn't run the code for a vision recognition system very easily 20 years ago.
Sure, yeah.
So the missing piece was laser ranging, or LiDAR. And so the way if you understand the way LiDAR figured into autonomy, vehicle autonomy, and the development of it, And you actually have a pretty good beat on how this came about. And it started at the Stanford Artificial Intelligence Laboratory called SAIL in about 1960-61, when a PhD student was tasked by NASA. And notice the 61, we did not have Apollo for a few. Kennedy had given his speech, but they were not very far along. They wanted to know whether they could get a moon rover, they could operate a moon rover autonomously from Earth, basically joystick it. The answer was no. But in the process, they built the Stanford cart, which was like the autonomous vehicle. It had bicycle wheels. It had a lead acid battery on it. It had cables connected to it because it couldn't process, or later it had a radio probably. But I think it was cables mainly, connecting it to the computing resource. And they used cameras to try to guide it. And it was really sloppy. There's some web. If you go into YouTube and look up Stanford cart, there should be, at least there were some really funny videos of this thing out in a football field. They drew like imagine a really drunk guy that lines football fields, going around with the thing to make it a really kind of a challenging path. And this, I don't know if it was a football field or what, but it was a field. Yeah. And this thing is just herky jerky trying to follow this line, right? That evolved in the late, I think it was 70s, it could have been 60s. A guy named Hans Moravec, who went on to be a professor at Carnegie Mellon, took charge of became a research bed, basically, for all these people that were doing really proto-autonomy work. And Moravec was using cameras, and to navigate your environment, you need to know where you are and what's around you. And you gauge that, and then you move to where you want to move. And then you do that again. Now, you and I do this really, really quickly, right? Moravec created, he was watching, I don't know if it was a chameleon, a lizard of some sort, with its eyes on the side of its head, right? So it doesn't have good stereoscopic vision. He had one camera, and doing stereoscopic vision processing kind of real time was just way beyond. These computers were like 1/500,000th as powerful as what's in your iPhone right now. You can't really conceive of how little processing power. And these were research systems, right? These were the best of the best. So he put this camera on a horizontal. Imagine a four-wheeled cart, 4 bicycle wheels, and in the direction that the cart's pointing, there was a silver bar that went horizontally across. And then the camera would move from place to place to place to place across that bar over a minute or so. And then it would post-process and it would move forward. It took 15 minutes for it to make one of those step-stop motions, right? 15 minutes. It took him so he got to the point, though, that he could put obstacles in a room, and the cart would be able to sort of navigate its way across a room in 5 hours. 5 hours, right? But that was the beginning of it. And slowly, LiDAR they realized that, well, if we have the laser, then we don't need to do the calculation. We'll know how far stuff away is. The issue was that the laser was a single point of light. So you had to do some games with, before it started at this point of light, and then it started scanning back and forth. So you'd have like a line of laser light that would go back and forth. Well, they took that line and they would rotate the line. If you imagine, take a pencil, hold it, and then turn it, or think of a propeller. Essentially, they propellered a line laser, and that propeller is your line. So suddenly you have more of a plane, I guess you'd call it, right? And I don't think you'd guess you'd call it. It is a plane, right? So they started using that. Moravec moved to Carnegie Mellon, and then Red Whittaker sort of took the reins with what became the Field Robotics Center. And if there's a father of modern autonomy, I think Red Whittaker would have to be called that. It was parallel development. But, and at the time, Sebastian Thrun, whose name you may know, he was the one who won the Dark Grand Challenge in 2005. And he went on to manage the SAIL lab at Stanford. He worked as a computer science professor at Carnegie Mellon. So a lot of the pioneering work went on there. And so one thing led to another. They got LiDARs from here and there. The military developed a LiDAR called the ARIM. It was a group that used to be Willow Run Labs in Michigan in the early to mid 1970s. They developed this LiDAR that could actually scan and create an image and spot, again, tanks is what they were looking for. Well, Whittaker's team got a hold of one of those guys, put it on a converted GMC truck, and then created the truck is full of computer equipment again, but that equipment is probably 10 times more powerful than the stuff that the AOL guys are using, right? It's just all these enabling technologies enable, better, faster, cheaper, right? Mm-hmm. This thing crawled along at like 5 miles an hour. So its step-stop. Moravec's took 5 hours to get across a room. These guys could put what was called NavLab 1 out on a road or wherever they wanted to put it. And it could move at about 5 miles an hour on its own. Okay. So that over time, the LiDARs kept improving. The DARPA Grand Challenge in 2004, which went by the debacle in the desert. I don't know if this is a little while ago, but DARPA, the Defense Advanced Research Projects Agency, it's the skunk works funder of the military. Like, what's this crazy far out idea? And in 2004, sending a bunch of cars autonomously across the Mojave Desert and expecting them to get anywhere near the destination was a crazy idea. I mean, nuts. Because the technology it really wasn't there. I mean, Red Whitaker's team and many others have done some great work. And nobody finished, right? This thing ends, the furthest anybody went was Whitaker's team, and they made it like 7 miles or something like that in 2004. And people derided it, right? This is a little before your time, but I wasn't into this stuff at all at the time. But I remember reading stories about, these guys can't drive. Autonomous cars are never going to happen, whatever. Well, part of the deal was, Travis, is you had the sensor packages the computing had gotten to the point where they could manage it, and the GPS was good. So you really needed good obstacle avoidance, right? So you knew generally where you were. You knew there was a hairpin up here, but is there a rock there? Is there another car there? Stuff like, is there a fence post there? And LiDAR is really good for that. So they were using it for your sort of intermediate range, but they had to use multiple LiDARs because they were line scanners that they were twisting or whatever. They were pretty basic deal. So they would have like 6 of these things, stuff that they'd adapted from SICK, which is a company founded by Erwin SICK. He's a German guy. He's not ill. But it was an industrial scanner that his company started his company to keep people from getting their hands cut off in industrial, and stamping machines. So they were adapting these things that were not made for vehicle autonomy, right? And airborne scanners, Regal is a company that's based in Austria that they were using. Red Whitaker used one of those on his. They were expensive and they weren't designed for it. Well, one of the contestants in the DARPA Grand Challenge in 2004 was a guy named David Hall. And David Hall was a brilliant engineer who had come to Silicon Valley from Boston and started something called Velodyne Acoustics. And Hall, his deal was they made subwoofers, really awesome subwoofers. So like, I don't have a really awesome subwoofer. And if you don't have a really awesome subwoofer, if you have your volume turned up, which at my age, we don't do anymore anyway. But if you do, and then there's a huge thump in the music, you get massive distortion. It sounds terrible, right? It's just like, and you do audio, He figured out a way to using, I can't remember the technology right now. He figured out a way to dampen that. And over time, he figured out a way to use digital signal processors to make that distortion basically go away. So audiophiles are like, this is the greatest subwoofer in the history of the world. Subwoofers are growing awesome. Well, by 2005, 6, 7, or 2004, say, and particularly as we moved into the 2008 era when the financial crash happened, the subwoofer business was not doing great. Everybody was going offshore. And Hall has got this factory space that he's not sure what to do with. He's like, I could use a military contract. Maybe I'll do a vision system. He got into like battle bots that he was using. I mean, this is a guy that could do whatever he wanted with things that are made of metal and glass. Point being, he invents a stereoscopic vision system that is pretty rudimentary, but he came in like 2nd or 3rd place before getting hung up on a rock of his own. So Whitaker's thing got hung up on a rock in 2004. Hall finished like 2nd or 3rd. He goes back to the drawing board and comes back in 2005, like 18 months later, with this spinning thing on the roof of his Toyota Tundra. He called and he had just come up with it. He'd had a conversation actually the previous year with a guy from Ford who had said, what we really need is this idea. And Hall had sort of been back in the back of his mind. And Hall was the kind of guy who could like say, yeah, I could make this. It had 64 lasers and detectors, and it spun like 20 times a second. Zoom, 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 zoom. And those lasers they were each associated with a detector. And using that, you had a 360-degree ribbon all the way around the vehicle, knowing where everything was every second of the way. So you didn't have to understand what you didn't have to like save off into memory. I just saw a bicyclist back here. You see the bicyclist over and over and over again, right? Which is a really big deal. It's called keeping state in the state of the art. So Paul puts this thing on the top of his Tundra for the 2005 race. He ends up not winning that. Stanford won the first one, and Red Whitaker's team won the second one. I think that's right. Yeah. But no, Whitaker didn't win that one either. Whitaker won the third one. I don't want to get into this, but the point is, Hall's LiDAR is like this. The angels sing. All these, they called it. Hall called it Woodstock for geeks, right? I mean, these were people whose names, if you're in autonomy, they were all there essentially. Mm-hmm. The guys that are running and the women that are involved in some of the biggest autonomy startups and have been subsequently bought by the likes of Ford and so on. We're all at this thing. Most of them were. So Hall comes back for the 2007 Urban Challenge, not as a competitor, but DARPA says, all right, everybody who competes gets one of these LiDARs. So Hall has remade this thing into what you've probably seen. It's like a conical, looks like a human head almost, except it's on top of the car and it spins around.
They're white generally, aren't they?
Silver, I don't know.
Okay.
They're different ones.
I think
now.
I've seen them, yeah.
So that design has been picked up by lots of different people in some iteration. And that is really, that LiDAR, David Hall's LiDAR, is what enabled the perception to be good enough for most of these teams that are continuing to develop this technology, vehicle autonomy, to do what they do. Mm-hmm. And Hall is now, it's called Velodyne LiDAR now. I think they still make, in China, subwoofers, but LiDAR is the business. They're going public in one of these reverse, special, what do they call it? SA. I don't know. They're going public. There's another one that's going public called Luminar. And yeah, it's the real deal now.
Man, okay. So that was kind of the limiter back then, was that they were kind of able to start to do the processing speed and all that kind of stuff, but they really needed LiDAR to give them an accurate image of what was around them. And that's what they were able to do.
Yeah. I mean, LiDAR took care of, with the help of, they were using visual cameras, they were using radar, but the sensor fusion and LiDAR being really the critical component was what got them out of the sort of garbage in, garbage out problem with vehicle autonomy. So it was truly a massively important sensor.
Right. Yeah. So do you, because I mean, like now, just kind of from my perspective, it seems like Tesla has the furthest step into kind of autonomy as like a company, I guess, or releasing to the, to consumers. But they don't have LiDAR, do they?
No. So Elon Musk my understanding is that they actually do use it in their testing.
Okay.
No, none of the production vehicles. I mean, Musk is right. LiDAR is that spinning thing on the top of these vehicles that Velodyne made was a $75,000 sensor, right? So It's not going to make sense, even in a robo taxi where you're, making money every time you drive. Mm-hmm. It's not going to make sense for a consumer vehicle. And so Musk is right in that, especially as he was developing these systems that didn't compute. The issue is, and Tesla's had a couple of accidents now where LiDAR would have probably saved the passenger. There's all these levels of autonomy, right? Tesla's at like level 2, which means you need to be paying attention as a driver.
Yeah.
Level 5 is you don't need a steering wheel because everything's going to be taken care of and you can drive somewhere that the vehicle's never been before and it'd be fine. Mm-hmm. What they're mostly shooting for is something called level 4 autonomy, where it's pretty well mapped. There needs to be a driver in there, but the car can do basically everything. Is Tesla ahead with autonomy? I think there's a lot of debate as to who's where. Waymo, the Google subsidiary, has driven millions of miles. Ford Argo AI has driven millions of miles. A lot of these folks, I mean, vehicle autonomy is being pursued passionately and with billions of dollars being spent annually by most automakers now. And all of them, but Tesla, that I'm aware of, are using LiDAR as one of their sensors.
Wow.
So David Hall had an interesting, I went and talked to him in Alameda, California for the book. And I asked him, do we need this now? Could we not use vision? And the truth is, for a lot of contexts, you wouldn't need LiDAR necessarily. But he had 2 points. One, the sensor is on the car now, pretty much. And there aren't a lot of cases where a useful sensor has been taken off a car. So there's precedent. There's precedent in the development of the algorithms and so on. So LiDAR is part of the package for a lot of systems that will help cars drive by themselves. And the third thing is, these accidents, and Tesla, I'm sure, has gotten better, but the last one is in 2019, and both of them involved trucks. And they were probably white truck, 53-foot tractor trailer beds on bright days. And the first one in Florida was in 2016, where it was a bright day. The cameras, the guy should have, first of all, they're not supposed to be driving themselves in these kinds of streets, but people naturally, it's like, my car drives itself. I mean, shoot, I'm gonna take a nap. Car mistook, couldn't see the truck because it was such a bright day, a bright sky, bright truck, white. Drove right underneath it, took the top of the truck and probably the top of the guy off, right? LiDAR would have spotted that. So there are specific cases where it's very hard to argue if LiDAR becomes something that's reasonably priced, and it looks like the costs are coming down. Okay. Because there's lots of competitors and the technology is understood. It's hard to argue like, I don't want that. I don't really want to know instantaneously everything around me. That I don't want, right? From a consumer perspective, I put my kid in an autonomous vehicle. I want it to have LiDAR. I don't really care how good your vision engineers are, because I want that backup in case, you get weird reflectivity, just weird things happen. And LiDAR has problems too. In a snowstorm, LiDAR is not terribly useful because it's hitting the snowflakes, right? Oh, sure, yeah. So you have very foggy situations. LiDAR is used in space, in orbital applications where you can't see through the clouds. So, man. So do you think that like kind of the when we first start to see, I mean, we're seeing autonomous cars and everything. Do you think kind of the first maybe commercial things that we start to see, or maybe the first robo taxis even, will have LiDAR on them? Oh yeah, totally. Yeah, I mean, because Waymo is running robo taxis as we speak in Mesa, Arizona, somewhere. They do a lot of it in Arizona for the early commercial applications because it's a grid and the weather's it's pretty predictable. Oh, okay. And so on. They're running them where just you and I could get. Yeah, they'll have a safety driver, but you can, as far as I know, unless they stop the program, they're running taxi services where there's a safety driver that's not doing a whole heck of a lot. That's cool. Occasionally there may be a weird situation that it has to jump in. It's just, the deal is, Travis, it's not even the 80-20 rule, right? Where, 20% of the work gets you 80% of the way there. It is like the 99.99.001 rule, where construction site on a snowy, weird day with a weird turn and a horse falls out the back of a, you know what I'm saying? Just these, and it's a different topic, but how do you deal with a situation where there's the babysitter pushing the baby carriage across the street and you're being somehow jammed over by a tractor trailer, and you've got to decide whether you, or it's the baby, it's your life or the baby and the woman's life, right? And so if I make that mistake and decide that instinctively, you don't have time to decide as a human being, right? Yeah. You maybe killed the babysitter and the baby. You're not probably going to go to jail if it wasn't, proven to be manslaughter or whatever. Right. What happens with a Google car in that position? Right? It'll happen because if you had everybody driving a robot, which is what an autonomous vehicle will be, probably the roads would be totally safe. The issue is we don't drive very well, right? Comparatively. I mean, we're good at really weird situations maybe, but we lose 10,500 people a year to drunk drivers here. 36,000 fatalities and 2.7 million injuries in the United States alone in vehicles in 2019, I think, or 2018, I think is the last data. So, it's a tough, the regulatory questions are really tough. Like, how do you manage that? How do you ensure that? Is Google liable if it goes through its calculation and says, I'm taking out the baby, right? Well, who's liable? You're not driving it. So these are questions that we will solve. They did the same thing when cars overtook horses at one point, right? There were no traffic lights back then. And we'll get through it. But there's a lot of questions that are non-technical in addition to the enormous technical hurdles that have to be overcome. Yeah. No, that's true. Because I'll always see, I'm driving with my girlfriend and I'm like, she's kind of on the fence about autonomous cars. And I'm like, wouldn't you rather have an autonomous car than that jackass up there driving? It'd be safer without him on the road. Yeah. Distracted driving is a huge issue. I mean, how many times have you sat at a light when it went green and just nobody's moving?
Yeah.
Right? Why aren't they moving? Because they're on their phone.
Right.
I don't know. Autonomous cars most likely will not be drinking, first of all. Second of all, they're not going to be on their phones.
Right.
So, and can they be hacked? There's tons of issues.
Scary stuff.
That surround it. Yeah. No. So.
Yeah. Well, I've heard it compared. It may have even been Elon Musk who said this, where, what's driving the car today is essentially just, two cameras that's on like a gimbal or something moving around, where if you could have a, LiDAR and all this other kind of stuff on there, it should be way safer.
It just makes it safer. Yeah. I mean, that's the ultimate thing. You're back to your tennis ball against the garage door thing. You know where everything is, assuming you don't have some exceptional situation. If you have, I'd say this though, if you have a snowstorm that's extreme enough that you can't go with LiDAR, then you probably you probably couldn't see it with your eyes either. You'd be in a whiteout and you would pull to the side of the road. So that's probably actually a pretty easy scenario for LiDAR. Mm-hmm. But yeah, I mean, it's another layer of sensing. And the challenge has been heretofore that layer has cost $75,000. And so LiDAR is Velodyne sells these things for a tenth of that now. But I think automakers are looking at ideally a price point of about $1,000 in addition to whatever else for a consumer vehicle, that they can add that to the price and the consumer's like, yeah, that's worth doing. You know what I'm saying? Probably could be more and will be more in the early years because it's mostly going to be, I would assume, commercial uses. It's, I rode in an autonomous vehicle. I don't know if you've ever been in one. Have you ever been one, Travis?
No.
In Pittsburgh. And that's where Uber's advanced technology group is testing these things out. And they chose Pittsburgh because it's 4 seasons. And I don't know if you've ever been to Pittsburgh. It's really quite a beautiful place, but it is hilly. The roads are nuts. I mean, there's roundabouts and lights and just, it's nuts. So they're putting these things to the test there. So yeah, we'll have to see where this goes, but I think that we're going to see LiDAR in cars hopefully sooner than later. And I'm not sure what the pandemic's done with the amount of research that's happening and the budget cuts that happen at places like Uber.
Sure. Yeah. Yeah. No, I'm definitely curious to see where this stuff goes and see how it gets implemented. So we talked about the iPhone and the iPad real quick, but why do they have LiDAR in there? What is it doing for the phones?
I think some of the reasons that they put it in is that, first of all, gaming. So the really near-term applications, because Apple's already kind of alluded to 3 or 4 of them, or those who follow this closely. One is like games. So there's like a lava game that people play on their phones, augmented reality stuff, where you hold the phone or the iPad up, point it in your room, and there's a gremlin in the middle of the room that's not actually. It's basically Pokemon Go type thing. Well, you need 3D photo. If you put your hand without LiDAR, if you put your hand between you and where that kind of gremlin looking thing allegedly is that your augmented reality system is putting there, your hand will not occlude the gremlin right now because the camera doesn't know where your hand is, right? The gremlin is going to be in that space. With the LiDAR, for example, on the Apple iPhone, say the iPhone 12, assuming they do it, you put your hand up and you would occlude part of the gremlin because the LiDAR knows your hands between you and where it is putting that fake gremlin in the room because it knows how far away your couch is because it's using lasers to do that. Now you can do it with the 2 cameras, but it's really immediate. And so that's sort of gaming. There's a bunch of applications like that. IKEA is interested in this and others because you could scan your room and then put a couch here or there or whatever because it knows exactly the dimensions, right? And then the third one that I saw was quite interesting. It was a health related application. They had a guy, this is, I think the stuff's on YouTube. If you look at Apple, iPhone or iPad Pro LiDAR, and there's a bunch of videos out there that kind of show how this works. But he's against a wall and he lifts his arm up. Like, let's say you had shoulder surgery and they're looking at range of motion. And as he lifts his arm up, you see a calibration showing you exactly how many degrees that arm is moving, right? And another application that is really easy to imagine is like Zappos or Stitch Fix, guys that are doing custom clothing, or in Zappos' case, you need to know your size. Right. If you scan your foot they're going to know your foot. I mean, you can scan the body, whatever. They'll figure out how they want you to scan it. They will know precisely how big your foot is If you have a bump on your foot, whatever. And if you were to drop to your skivvies and get laser and have someone laser, so you set your phone up, turn in a 360 and hit save, then they'll know precisely your measurements for a custom suit or custom anything you're going to wear.
Right.
So I think those applications, if you come back in 10 years and listen to this thing, which everybody should definitely do. But if you were to come back and listen to this, it'd be like, that is so uncreative. That is so lame that you can come up with these ideas. Because the truth is, this is a tool that people who are doing things that you and I have really not thought much about are like, oh, that's a big deal. What you're doing is democratizing LiDAR. You're democratizing the laser tape measure. And who the hell knows where this is going to go? I mean, the people at Hughes, the guy that invented the laser, could not have imagined that you can put, a LiDAR on a phone, or that you can map Mars with it, or whatever they're doing with this technology now. And it's going to be exactly the same deal.
Man, that's awesome. Yeah, it totally makes sense to use it for AR related stuff, but then the availability to scan things around you and everything. So that makes sense. That's going to be so fun to see what, these third-party app developers come up with if they have access to that kind of, equipment in there.
Absolutely. It's a new tool. It's a fundamentally interesting tool that creative people will take in directions that we can't predict very simply. So, and it's exciting. I mean, I think it's cool. You could look at it like, oh, another thing on the, bell whistle on the iPhone. But I really think this bell or whistle is going to be much more meaningful and useful than people can imagine at the moment.
Right. Yeah. Man, cool. This is exciting. Thanks so much, Todd, for sharing all this stuff. I love it. It's great to hear this stuff. It gets me so excited for future tech. I just want to hear right now. Yeah. No, thanks for doing what you're doing, Travis. It's a great podcast, and it's a real pleasure to be here. Heck yeah. Yeah. Thank you. And your book, that's called The Laser That's Changing the World, The Amazing Stories Behind LiDAR from 3D Mapping to Self-Driving Cars. Where should we send people to grab a copy of that? Yeah, I mean, just Amazon. And it's available in Kindle format too. I don't think there's an audiobook, but yeah, I mean, you can do the print copy, you can do Amazon. And then my website, toddneff.com. Yes. The reason that I mentioned it is that the section of the website that deals with the book, if you happen to pick it up, I have a ton of photographs that I took when I was reporting in the extras section. So you can see the people that I write about. Yeah, I've been through that. So we'll have links for people listening. We'll have a link to your book on Amazon and your website, so people can check all that stuff out. But perfect. Yeah, thanks so much, Todd. This was fun. Appreciate it. Travis, great, man. Cool. Well, have a good one. All right. You too.